In this video, we solve problem number 3 from quiz number 3 from the spring 2021 semester for elementary differential equations at Tulsa Community College. Now, there were multiple forms to this quiz, so you may not have seen this exact problem, but some students in this class saw this problem, and the problem statement says this. When a cake is removed from an oven, its temperature is measured at 300 degrees Fahrenheit. 3 minutes later, its temperature is 200 degrees Fahrenheit. Assume that the time rate of change of the temperature of the cake is proportional to the difference between the cake's temperature and the room temperature. Assume that the room temperature is a constant 70 degrees. In part A, we're asked to set up an initial value problem describing the temperature in degrees Fahrenheit of the cake as a function of time with temperature measured in minutes. Then we're asked to solve for T of T, and then we're asked how long it will take to cool the cake to 71 degrees Fahrenheit. Okay, so that's room temperature, or 1 degree warmer than room temperature. Well, first let's state everything that's given, and then we'll use the given information to set up the initial value problem. Now remember, they're asking us for temperature in degrees Fahrenheit as a function of time with time, or this says temperature measured in minutes. It's time measured in minutes. Sorry about that. So T is temperature of the cake in degrees Fahrenheit. T is the number of minutes since the cake was taken out of the oven. Given that, let's see what the problem statement says. It says, when a cake is removed from the oven, its temperature is 300 degrees Fahrenheit. Since little t represents the number of minutes since the cake was removed from the oven, the moment the cake was removed from the oven corresponds to t equals 0. So they're telling us here, this first sentence, that the temperature at time t equals 0 is 300 degrees. So we would represent that symbolically as t of 0 equals 300. Then it says 3 minutes later, and t is measured in minutes, so it's going to tell us something about the temperature 3 minutes later. The temperature of the cake is 200 degrees Fahrenheit. So at this time, 0 minutes or 3 minutes, the temperature is 300 degrees Fahrenheit or 200 degrees Fahrenheit, respectively. Okay. Then it says, assume that the time rate of change of the temperature of the cake is proportional to the difference between the cake's temperature and the room temperature. So the first part of the sentence says, assume that the time rate of change, of temperature of the cake, so that's change in temperature per unit time, is proportional to, so that means it's equal to a constant times the difference between the cake's temperature and room temperature. So the cake's temperature is represented by this capital T, and room temperature, they tell us, is a constant 70 degrees. So that is our differential equation. We can solve this differential equation for t in terms of t. It will have a constant of integration in it. It will also have this constant k of proportionality. The fact that they give us two conditions will allow us to find both the constant of proportionality k and the constant of integration, and that just comes from solving the differential equation. So if you're thinking, why do I need two of these? It's because we have two variables, the constant of proportionality and then the constant of integration that just comes from solving the dE. So, okay, what did it say in part A? Set up an IVP describing the temperature of the cake as a function of time with time t measured in minutes. Well, I think we're pretty much done with A. We've got T of t equals k times, the temperature minus 70, and T of 0 equals 300. Keep note of the fact that T of 3 is also equal to 200, and that is going to allow us to find K. You might think of this as a boundary value problem, but that second point is really just allowing us to find k. And then part B says solve for t. Well, if I want to solve this differential equation for t, it's just it's a separable differential equation, so it's relatively easy to solve. Let's see. We stated the given information. What else did we do? We translated the English sentence into a differential equation. And then we stated the initial value problem. And then for part B, we are going to solve this initial value problem for t of t. So the first thing that we'll do is we'll solve for t. Just solving the differential equation, it's going to have two arbitrary constants in it, and we'll use those conditions to find the constants. So I have dt dt equals k times the quantity t minus 70. That's separable. So we will separate the variables to solve. So to get the little t's on this side, I'll multiply both sides by dt. In order to get this capital T on this side, I will divide both sides by the expression t minus 70, or multiply by 1 over t minus 70. That's the same thing. So these guys undo each other. And we have this 1 over t minus 70 times dt equals k times dt. Of course, those are different dt's. Now that the variables have been separated, we just anti-differentiate. You anti-differentiate each side with respect to the variable that is on that side. This one is pretty easy to solve. Well, they're both easy to solve. We don't have a basic rule for this, but if we use a u substitution, we do. If we let u be the denominator, then du is just the derivative of that times dt, so it'll be 1 times dt. So that's our u, and that is our du. Turns out this time that du and dt are exactly the same thing. So we end up with the integral of 1 over u times du. And that's easy enough to solve. We've got a rule for that. The antiderivative of 1 over u is the natural log of the absolute value of u plus c, but we're going to let the constant of integration on the right absorb the constant of integration from the left. And u is t minus 70. The antiderivative of k with respect to t is k times t. Don't forget your constant of integration. Okay. And then we're trying to get t by itself, so we will exponentiate. E to this power equals e to that power. And because of the nature of the natural logarithmic function and the exponential function with base e, these guys undo each other. And we'll just have the absolute value of this over here. Now let's see, what were we doing? We anti-differentiated. And then we back substituted for the u substitution. And now we're solving for t. Okay, so we had the absolute value of t minus 70 equals e to the kt plus c. That means that t minus 70 equals plus or minus e to the kt plus c. Well, since I have a sum of exponents there, kind of like this rule from algebra. If I have two expressions that have the same base, whether those are exponential functions or power functions, if the base is the same, you add the exponents. That's true for exponential functions as well. So typically we would go from this right-hand side to the left-hand side, but we can also go the other way. So this is going to give us this. We'll have e to the kt times e to the c e to a constant power is just another constant, plus or minus. That constant is just another constant, third constant. So we'll just call that C1 times e to the kt. And that's equal to t minus 70. And then if I want to get t by itself, I just add 70 to both sides. Okay, so we just did a bunch of algebra to solve for t, but it has two arbitrary constants in it. We will use one of our conditions to find either C1 or K, and then we'll use the other one to find the other one. So that's the plan. I wrote ICs, but I guess technically they're boundary conditions. In this context, excuse me, I'm really thinking of it as an initial value problem, and the second condition is just helping me to find the value of that parameter. But I guess technically for differential equations, since we've got two values of the independent variable, they would be boundary conditions. So we have t of 0 equals 300. Well, that's the same as saying this. When lowercase t equals 0, so that means that t equals 0 minutes, as soon as we remove that cake from the oven, the temperature is equal to 300 degrees Fahrenheit. And so we can use these to solve, or at least get an equation involving C1 and K. Let's see what happens. If we evaluate this expression at t equals 0, get this. And we know that e to the 0 is 1. So this is actually pretty simple. T of 0 turns out to be 70 plus C1, regardless of what that initial temperature is. But we're told that the initial temperature is 300 degrees, and that's enough to allow us to find C1. So we'll set these guys equal to each other. Now I've got a very simple equation for C1. So I'll solve it for C1 by subtracting 70 from both sides, and we get 230. So we have T of t equals 70 plus 230 times e to the kt. All right, we're still not quite there yet. We need our constant of proportionality, but that first condition allowed us to find C. Maybe our second condition will allow us to find K. Our second condition was this: at t equals 3 minutes, the temperature of the cake was 200 degrees Fahrenheit. Okay, so we can replace t, lowercase t, with 3 and set capital T equal to 200, and then we'll have an exponential equation that we can easily solve for K. So we have T of 3 equals 70 plus 230 times e to the K times T, and T is 3. Okay, so we have that, and that has to be equal to 200. So we're saying to ourselves, well then in that case, what does K have to be? So now I'm almost ignoring everything else, and I'm thinking of this as a single equation, and I'm solving it for K. So the first thing that we do when we're solving an exponential equation is we isolate the exponential term. So we will subtract 70 from both sides. 200 minus 70 is 130. And then we will divide both sides by this 230 because we're trying to get the exponential by itself. So we've got that. These guys reduce. And of course, you can divide the numerator and denominator by the 10 there. And so we have this. And then if we want to get K by itself, we need to get it out of the exponent. One way we can do that is to take the natural log of both sides. The natural log of e to some power is just the power, because this exponential and that logarithm are the inverse functions of each other. So if we apply one and then the other, they undo each other, and you just end up with whatever you started with. And so it turns out that K is equal to 1/3 of this. So you can take that and divide by 3, or you can multiply by 1/3. I think I prefer to multiply by 1/3 because it makes it look a little cleaner. Now, if you want a decimal approximation, you can get a decimal approximation this way. So we'd have 1 divided by 3 times the natural log of 13 over 23. And that is approximately negative 0.91 or 19, excuse me, 02. Okay, so T of t is equal to this, but k is equal to 1/3 of this natural log, the natural log of that number. So we have 70 plus 230 times e to the k t. Or if you would prefer the approximation, and some people do, that's fine. That is our temperature as a function of time. Either one is fine. So we used the first initial condition to find C1, and then we substitute C1 into the form of T of t. So we knew the general form, we just weren't sure what the C and the K were. So we found C, then we used the second initial condition to find K. And that required solving this exponential equation. And then we substitute K into the form of the solution. And now we don't have any arbitrary constants in it. We've got this constant and this constant. Now this is just temperature of the cake as a function of time. If you give me any time, I can tell you what the temperature of the cake ought to be. Now, if somebody asked you, how long will it take to cool to room temperature? How long will it take the cake to cool to room temperature? Know that it would never cool to room temperature because this exponential function is always going to be a tiny positive number. After a little while, though, this is going to be so close to 0 that we're basically at room temperature. But it will never actually get to 70 degrees because this is always positive. This exponential function is always positive. But in the limiting sense, as t goes to infinity, in an infinite amount of time, the temperature of the cake approaches room temperature. The question says, how long will it take to cool to 71 degrees? So it's almost room temperature. So we're almost saying, how long will it take for this piece to be 1 degree? So it'll be 70 plus 1 degree would be our 70 degrees. Well, let's figure that out. When it says how long will it take, that's asking for a time. And this is telling us that the temperature is going to equal 71 degrees Fahrenheit. So we just replace T with 71. And then we solve for little t. And you can use that logarithmic expression if you want to, or you can just use this decimal approximation. I'm going to use the decimal approximation this time. So if we subtract 70 from both sides, we end up with this exponential equals 1. And we want to isolate the exponential, so we'll divide both sides by 230. And we're trying to get t by itself, and it's in the exponent for an exponential function. So we will take the log of both sides because logarithmic functions and exponential functions undo each other as long as they have the same base. And then we'll just have this constant k times t equals that. And of course, this is all approximate because our K is approximate. Then I guess the entire model is approximate, so that's fine too. So T would be equal to this. This is a number of minutes. Now, if you prefer, you could substitute in K, which is that 1/3 of the natural log of, I think it was 13 over 23. So if you want to be more accurate, you could use this one instead. But you don't have to, you could just use that. So let's see, we've got natural log of 1 over 230, -5, divided by -0.1902. So about 28 minutes. 28.6 minutes. Or let's try it the other way. If we have natural log of 1 over 230, if we're dividing by 1/3, that's the same as multiplying by 3. Let's take that and divide by that result and divide by a natural log of 13 over 23. And see if we get the same answer either way. I think that the difference between the answer from this and the answer from this is off by 0.03, or excuse me, not 0.03, 0.001, like it's that order of magnitude. So yeah, either one of these is fine. So it would take about 28 minutes to cool to 71 degrees. And so that is that application problem from the quiz number 3. Again, we just look for the given information. We take the differential, or we take this statement in the differential, or excuse me, take the statement in the problem statement, and we write it as a differential equation. And then once we have the differential equation and these conditions, we've got our IVP. So then we solve the differential equation, happens to be separable, so we separate the variables. And then after we separate the variables, our solution has 2 constants in it, one which was a constant of integration, and then the other constant was the constant of proportionality. We use the 2 conditions to find both constants, and that gives us our temperature as a function of time, and then we can answer all kinds of questions. If you give me a time, I can tell you the temperature of the cake. If you ask me what time the cake will be a certain temperature, I can answer that as well. I can talk about what would happen to the temperature of the cake after a really long time, which is the limit of this as t goes to infinity, which is 70. So after a really long time, the cake will approach that room temperature. But it's almost room temperature. It's 71 degrees after 28 minutes. That's what that says. So we were able to solve that part of the problem and see that we're at nearly room temperature after a little less than a half hour.